For over a century, flight has obeyed one unbreakable rule. Aircraft need fuel. Jet fuel, aviation gas, stored energy, something must burn, discharge, or be consumed to lift metal into the sky. Every aviation breakthrough, no matter how advanced, still bowed to that law. Until one flight made people question whether that rule was ever absolute. When footage began circulating of an aircraft lifting off without visible fuel systems, without conventional batteries, and without refueling infrastructure, most experts dismissed it instantly. Impossible. Misinterpreted. Staged. But then the name behind it surfaced. Maxwell Chikumbutso. The same inventor already associated with unconventional energy systems. The same figure whose work had quietly unsettled engineers before. This time, the claim wasn't about generators or vehicles. It was about flight itself. The aircraft was small, experimental, and intentionally unremarkable in appearance. No futuristic wings. No dramatic design cues. Almost as if it didn't want attention. But what mattered wasn't what it looked like. It was what it did. According to observers present at the test, the aircraft didn't rely on onboard fuel tanks. There was no visible combustion system. Instead, the focus was on something far less understood: radio frequency energy, RF waves. Energy that already fills the air around us, invisible, continuous, and largely ignored as a power source at scale. The idea sounds implausible at first. RF energy is typically weak, scattered, and difficult to harvest efficiently. Most systems that attempt to use it produce only milliwatts, enough for sensors, not aircraft. That's why aviation engineers initially laughed it off, until the aircraft moved. The test environment was controlled. Winds were light. Conditions were documented. Observers noted that the aircraft's systems powered on without any visible energy input. No engine roar. No exhaust. Just a low mechanical hum as control surfaces responded. Then came the moment that changed the conversation. The aircraft began to roll forward. Slowly at first. Then with intent. No external push. No tow. And when it reached takeoff speed, it didn't hesitate. It lifted cleanly off the ground and climbed, steady, controlled, and stable. Not a hop. Not a glide. A sustained lift. Engineers, watching, struggled to categorize what they were seeing. If the propulsion wasn't chemical and the energy wasn't stored conventionally, then something else had to be happening. Something drawing power continuously rather than consuming it. That's where Maxwell's RF system entered the discussion. The theory, as described by those familiar with the project, wasn't about capturing stray signals randomly. It was about structured RF harvesting, directed fields, resonance alignment, and conversion systems designed to pull usable energy from the environment at levels far beyond what traditional models predicted. Skeptics immediately pushed back. Physics has limits, they argued. Conservation laws don't bend for innovation. But supporters countered with a simple point. The aircraft was airborne. Data logs showed sustained operation. Control responsiveness. No rapid depletion curve. No thermal signatures associated with combustion. Whatever was powering it, it wasn't behaving like fuel. Behind the scenes, discussions grew more serious. Because if RF energy could be harnessed at this scale, it wouldn't just challenge aviation, it would challenge how energy itself is defined in motion-based systems. And this is where the implications quietly expand. If an aircraft can remain powered as long as it stays within an RF-rich environment, if propulsion no longer depends on carrying energy, but accessing it, then endurance, range, and refueling cease to be limiting factors. Military analysts began asking uncomfortable questions, not about speed, but persistence. Civil engineers wondered about drones, cargo platforms, and high-altitude systems that never need to land. Meanwhile, Maxwell said very little. No dramatic claims. No bold declarations. Just continued testing, refinement, and silence. And as more observers reviewed the footage, one detail became impossible to ignore. The aircraft didn't behave like a prototype straining against limitations. It behaved like a system operating well within its comfort zone. That question lingered, attention shifted away from the aircraft itself and toward the infrastructure surrounding it. Observers began noticing equipment positioned around the test area, structures that didn't resemble traditional ground support but also weren't typical communication arrays. To most people, they looked ordinary. To RF specialists, they looked deliberate. This wasn't just an aircraft experiment. It was an ecosystem. The system appeared to rely on carefully managed RF environments, where transmission, reflection, and resonance worked together rather than against each other. Instead of broadcasting energy outward and losing most of it, the setup seemed designed to shape the RF field, creating zones where usable energy density was far higher than expected. That detail mattered, because it suggested the aircraft wasn't breaking physics so much as operating in a space where the rules were being applied differently. Not violated, rearranged. As engineers rewatched the footage frame by frame, another anomaly stood out. During ascent, there was no spike in power draw. No surge typically associated with takeoff. The energy profile remained smooth, almost flat, as if lift wasn't a moment of strain but a continuous state. That alone challenged decades of propulsion assumptions. In conventional aviation, takeoff is the most demanding phase. Engines work hardest. Fuel burns fastest. Systems operate near their limits. But here, lift appeared to be just another operating condition, no more stressful than level flight. Behind closed doors, discussions grew quieter and more cautious. Not because answers were found, but because too many questions remained open. If RF-powered propulsion scaled even modestly, it could redefine endurance missions, surveillance platforms, and autonomous flight. Aircraft that don't refuel don't need runways in the same way. They don't need logistics in the same way. And they don't obey the same operational timelines. Meanwhile, Maxwell's team continued testing under different conditions. Different frequencies. Different field geometries. Different altitudes. Each variation refined the system, tightening control and improving stability. What stood out most to those watching wasn't speed or altitude. It was consistency. The aircraft didn't behave like a fragile experimental craft. It behaved like a platform being tuned for reliability. And that suggested intent. Because experimental breakthroughs usually chase proof. This system seemed to be chasing repeatability. The kind required not for demonstrations, but for deployment. As whispers of additional prototypes circulated, so did speculation about what roles this technology was truly meant to fill. Cargo platforms that stay airborne indefinitely. High-altitude observation systems that never rotate crews. Emergency response aircraft that don't wait for fuel clearance. Each possibility carried implications far beyond aviation. And yet, the most important detail remained unresolved. The aircraft only worked within certain RF conditions, which meant the future of this technology wasn't just about vehicles, it was about environments. About how energy fields are created, controlled, and shared. That realization reframed everything. Once that invisible architecture became the focus, the conversation shifted again. The aircraft was no longer the headline, it was the proof. What mattered now was the space around it, the unseen framework that made sustained flight possible without a drop of fuel. Experts began describing it not as propulsion in the traditional sense, but as energy immersion. Instead of carrying power on board, the aircraft existed inside a structured field where energy was continuously available, like a boat floating on water rather than carrying water with it. That analogy unsettled a lot of people, because aviation has always been about storage. How much fuel you can carry, how efficiently you can burn it, how far it will take you. This system removed storage from the equation entirely. If the field was present, the aircraft functioned. If it wasn't, it didn't. That dependency raised new questions. Could these RF environments be expanded? Could they move? Could they be layered, mobile, or adaptive? And most importantly, who would control them? Observers noticed that later tests weren't just about flight duration anymore. They were about boundaries. How far could the aircraft move before performance changed? How quickly could the system adapt to shifting RF conditions? Could the craft transition smoothly between zones without loss of lift? The answers weren't spoken publicly. But the tests told a story. Each iteration pushed the envelope farther. Transitions became smoother. Stability improved. The aircraft behaved less like something reacting to its environment and more like something integrated with it. That integration hinted at a deeper design philosophy. Maxwell wasn't just solving a power problem, he was rethinking how machines interact with energy altogether. Instead of extraction, the system relied on alignment. Instead of consumption, synchronization. To traditional engineers, that sounded abstract. But to those watching the aircraft rise, hover, and maneuver with calm precision, it looked very real. And then there was the silence. No formal papers. No patent rush. No public demonstrations aimed at applause. Just continued testing, refinement, and quiet iteration. The kind that suggests the real work is happening beyond the prototype stage. Some analysts began to speculate that aviation wasn't even the end goal. That flight was simply the most visible way to demonstrate the principle. Because if RF energy could be structured densely enough to lift an aircraft, it could potentially drive other systems, vehicles, platforms, even infrastructure, without onboard fuel or batteries. That possibility reframed the entire project. The aircraft wasn't the destination. It was the message. And as tests continued under increasingly complex conditions, one pattern became clear to those paying close attention. Every successful flight wasn't pushing the limits of the system. It was confirming them. As that question echoed through technical circles, the scrutiny intensified. Analysts stopped treating the project as speculative and began treating it as something already ahead of public awareness. The absence of bold claims now felt deliberate, not cautious. Almost strategic. Because breakthroughs that announce themselves too loudly tend to attract resistance before they're ready. This one seemed to be maturing in silence. Observers noticed that testing locations changed. Not dramatically, but intentionally. Different terrains. Different RF backgrounds. Urban noise, rural isolation, variable atmospheric conditions. Each environment posed new challenges, and each time, the system adapted. The aircraft didn't just tolerate these changes, it learned from them. That adaptability hinted at something deeper embedded within the system. Not just hardware, but intelligence. Algorithms capable of sensing field density, adjusting resonance, and maintaining alignment in real time. The aircraft wasn't simply powered by RF energy, it was negotiating with it. This blurred the line between propulsion and perception. Flight was no longer a brute force act of pushing air downward. It became a dialogue between machine and environment. Engineers began asking whether the aircraft even needed traditional wings in the long term. If lift could be maintained through sustained energy alignment, then aerodynamics might become secondary rather than central. That idea alone challenged a century of aircraft design. And yet, the current prototype still looked conservative. Almost intentionally familiar. Fixed wings. Standard control surfaces. As if the design was meant to reassure rather than provoke. To say, we're not breaking everything at once. Behind the scenes, however, development appeared to be accelerating. Power margins increased. Stability windows widened. The aircraft stayed airborne longer, not because it needed to prove endurance but because there was no reason to land. That detail unsettled aviation planners more than anything else. Aircraft are built around schedules, fuel cycles, maintenance intervals, crew rotations. Remove fuel from the equation, and the entire rhythm of flight changes. Now imagine platforms that stay aloft for days, weeks, longer. High-altitude systems that don't descend. Observation platforms that never blink. Emergency response units that deploy instantly and remain available indefinitely. These weren't distant hypotheticals anymore. They were logical extensions of what had already been observed. And through it all, Maxwell remained absent from the narrative. No interviews clarifying intent. No press releases tempering expectations. Just data, demonstrations, and silence. That silence did something curious. It forced the world to speculate without guidance. And speculation, when unanchored, tends to drift toward extremes. Some dismissed it outright. Others began quietly planning around it. Because in innovation, disbelief is cheap, but preparedness is expensive. And as the aircraft continued to fly, calm, stable, unbothered by the assumptions surrounding it, one thing became increasingly difficult to deny. That realization changed the tone of every conversation surrounding the project. This was no longer framed as an experiment searching for validation. It felt more like a chapter being revealed late, after earlier pages had already been written somewhere else. Attention turned to timing. Why now? Why reveal flight at this moment and not earlier? Some analysts suggested the answer wasn't technical at all, it was strategic. Because once a system like this becomes public knowledge, control becomes the real challenge. Not how it works, but how it spreads. RF-powered flight doesn't scale the way fuel-based systems do. You don't just build more engines, you shape more environments. That means infrastructure, coordination, and governance. It means that the most valuable asset isn't the aircraft, but the network that sustains it. And networks change power dynamics. Those watching closely began to connect dots between seemingly unrelated developments: quiet investments in RF research, sudden interest in spectrum management, unexplained upgrades to transmission infrastructure in regions far from major aerospace hubs. Individually, they meant nothing. Together, they suggested preparation. Meanwhile, the aircraft itself continued to evolve, but subtly. No dramatic redesigns. No radical departures from the original frame. Instead, refinements. Weight reduction here. Field stability there. Control response smoothed to the point where the aircraft appeared almost effortless in motion. Pilots who observed the tests described something unusual. Not excitement, not adrenaline, but calm. The aircraft didn't feel like it was fighting gravity. It felt balanced, as if lift was the default state, not something being constantly re-earned. That sensation raised a deeper question. If machines can exist in sustained energetic balance with their environment, what other systems might be redesigned the same way? Transportation, power generation, even cities themselves. Because the core principle wasn't flight. It was alignment. And alignment, once understood, is transferable. This reframed Maxwell's work entirely. The aircraft wasn't a weapon. It wasn't even a vehicle in the traditional sense. It was a demonstration of a new relationship between technology and energy, one where motion, endurance, and stability emerge naturally when systems are tuned correctly, which made the silence surrounding future plans even louder. No roadmap was shared. No milestones announced. Yet the pace of testing suggested urgency, not panic, but purpose. As if the window for quiet development was narrowing, and the world would soon notice whether anyone was ready or not. Because once energy no longer needs to be carried, once machines no longer depend on depletion, the question stops being how far can we go? That question lingered long after the aircraft touched down, if it could even be called a landing, rather than a pause. Because what had been demonstrated wasn't just sustained flight. It was sustained possibility. In the old world, limits were clear. Fuel ran out, batteries drained, systems degraded. Every machine was built with an ending in mind. But what unfolded here suggested a different framework, one where duration was no longer the primary constraint, where operation depended not on consumption, but on continued alignment with an energy-rich environment. And that changes everything. Because when endurance stops being rare, strategy changes. When persistence becomes normal, assumptions collapse. Aviation doctrines, logistics chains, even the economics of mobility all hinge on one fragile idea, that energy is scarce on board. Remove that, and entire industries must rethink themselves from the ground up. What made this moment even more striking was how quietly it arrived. No spectacle, no countdown. Just an aircraft rising into the air and refusing to obey expectations. Not aggressively, not dramatically, simply calmly. That calm was the real shock. It suggested maturity, intent, a system past the point of discovery and deep into refinement. And refinement only happens when the core problem has already been solved. Whether this technology spreads openly or selectively remains unknown. Whether it reshapes civilian life first or appears in places we don't see is still an open question. But one thing is already clear to those paying attention. The future of flight may not be louder, faster, or more powerful. It may be quieter, more patient, almost invisible. Because the real revolution isn't the aircraft you can see. It's the energy you can't.